Hello and welcome to today's webinar entitled Journey Through the Cloud Cost Optimization. My name's Ryan and I'm your host today. I'll take you through the topic of cost optimization within AWS. Today's webinar is the last in our Journey Through the Cloud series, so thank you for joining this morning. Our agenda and the purpose behind these webinars is really to educate you on common use cases, stepping stones, and the learnings that other customers have made through their journey into the cloud, giving you some best practices that will hopefully bootstrap you and your projects and your route through to being cost optimized, in this case, in AWS. Cost optimization as a topic today it's a key step in the cloud journey. So it's a point in time within the cloud journey that many people sit back and look at how they realize a cost-aware architecture within AWS. And today's webinar is about understanding those properties, how to use Elasticity to gain some real and measurable benefit, and ultimately to enable you to do more in AWS whilst using less, become efficient in your operations. So with that in mind, today's agenda is in three simple parts. It's talk about the fundamentals of AWS cost optimization, the properties of AWS that you can leverage to enable you to be cost efficient. And then we're going to talk in 5 steps how you can achieve cost optimization, and then give you some tips on where to go next. So let's look firstly at the fundamentals of cost optimization and why we want to achieve cost optimization. Firstly is that AWS is a utility. So just as you would turn off an electricity switch when you're finished using it, or lights when you leave the room, as a utility, compute and storage can be turned off too. So it should be a natural part of your thinking around architectures and application deployments that not only can you consume cloud resources very easily, but you can turn them off or throw them away when you're done just as easily. And this drives a fundamental optimization within the cloud, not only about the resources you're using to get a workload done, but of course because you pay for a utility as you use it, the price you're paying and the costs you're incurring. Secondly, efficiency. When you're being efficient with the resources you're using, you're therefore being efficient with the price you're paying and the costs that you're incurring. You can do more within a given budget. So if you think about how you might budget for on-premise fixed resources, you have a certain cost that you need to be working within. And if you translate that into working within AWS, where you have variable costs, if you can keep your variable costs low at particular times of the day, the week, the year, then you release essentially budget to do more things. You become more agile, you can spin up more environments, you can try more things out within AWS. So you can become more efficient and agile by focusing on cost optimization. And then lastly, cost optimization drives 21st century architectures. It drives a number of the things that will help you achieve very high scale elastic applications, because cost optimization is all about bringing resources on when you need them and turning them off when you don't. This leads you into stateless, high-performance web application architectures. It leads you into disposable environments and a dev test environment. It leads you to disaster recovery environments that are turned off unless you need them. So it drives architectures that are cost-aware, and these are fundamentally modern architectures within AWS. So there's some key fundamentals here. Turn off the lights. When you stop using EC2 resources, you stop paying for them. So an EC2 instance that of any size, when it's stopped, you stop paying the instance hourly price, and you only pay for the storage of the EBS volumes if they're EBS-backed instances behind the scenes. So you might have a couple of 1 terabyte drives on an instance. You'll pay for the storage of those EBS snapshots only, and the EBS volumes only. You won't be paying for any traffic to the EBS, you won't be paying any hourly rate for the EC2 instance. So turning off the lights can fundamentally save you a lot of money, and that's going to be a theme that we're going to see throughout this presentation. Being elastic is another fundamental. So you want to be able to support workloads with the right amount of horsepower to get a job done. So provisioning just the right amount of compute power or the compute storage that goes with that compute to get any particular job done. So whether that be a batch processing job, whether that be handling a peak of web traffic on a web application, whether that be creating a disaster recovery capability to handle a portion of your users in your back office, for example, you want to be able to do that on an elastic basis and spin up the resources that are required to get that job done and no more. So following the demand curve, if you like, by being elastic. And you want to continually optimize as a fundamental here. So you can drive recurring and improving savings through these cost-aware architectures. So if you know what metrics are driving, if you like, the computational density in your application, the number of, for example, concurrent users that you can support on a particular application, the number of transactions you can process given so much EC2 resource. If you understand these sorts of metrics, you can continually refine the type of application architecture, the instance types, the number of those that are in play at any given time to drive huge efficiencies and to keep changing the dynamics of your cost base. So as we introduce, for example, new instance types, if you understand the metrics, you can map those to new instance types and understand whether they're going to yield you further savings in the future. And I'll look at some examples of that throughout this webinar today. Okay, so fundamentals kind of out of the way, let's look at 5 steps for cost optimization. And the 5 steps are going to be implementing elastic capacity and giving you some examples of what you can yield with implementation of elastic capacity. We're going to look at instance types and some of the dynamics around choosing different types of instances. And then we'll look around reserved instances where you can reserve essentially a lower rate or lower price point on an instance type in a given region and availability zone. And then we'll delve into the spot market and look at how customers are leveraging the spot market and some of the strategies around playing with the spot market and how you can achieve some savings there. And then some ideas around the use of services rather than software, and to give you a couple of examples of how that can save you money in a real term. So the first of those is elastic capacity. So let's have a look at this. So let's take a typical chart of server load, and shown here is a 24-hour period for a fictitious application. And the server load grows over time, and we can see that in the morning it starts to shoot up there to a maximum around the middle of the day, and then in the evening it tails off. So if we were to support that, and let's say we can support that with a capacity of 1 server shown there on the graph, we can have a traditional capacity required would be 2 servers. So my chart is too high in terms of server requirements. If I were to supply instances to support that load, I would require 1 server for 8 hours. So the first portion of my day I can achieve or support the load with 1 instance in AWS. As I go through the day, I would add another server for 8 hours, or 2 servers during the peak, and then in the evening I could support the load with just 1 server again. So we can see here that 4/6 of my time is taken up with servers, so I'm essentially making a saving of 1/3 by turning off an extra server during the first 8 hours and the last 8 hours of this 24-hour period. So an example where we can follow the curve with a unit of resource, in this case an EC2 instance that can support half of my load at peak. And by turning off that instance or the second instance during the morning and the evening, I can make 1/3 savings of my cost base for running that application. Looking at that in reality and how people achieve that, if you take a typical architecture, here I have mywebsite.com fronted by an elastic load balancer. So an elastic load balancer, the idea being that it's a regional service that can load balance my resources across availability zones at the back end. And shown here I have a single EC2 instance in an auto-scaling group that at 2 AM in the morning, as per my previous example, I have 1 of those instances to support my load. And as I go through time, of 8 AM I will grow, because 8 AM on my previous chart was the trigger point of requiring a second instance to do the work. Now this can be triggered in a number of ways. This could be triggered by schedule, because I just know when my peak is coming. But more likely that auto-scaling group will generate an aggregate of CloudWatch metrics. So shown there as little green charts on my EC2 instances, I'll be measuring, for example, the average CPU across the group. So in the first instance, it will be one instance. When that CPU rises to a level, let's say 80% CPU, it will trigger the creation of a second instance based upon a machine image, a saved image containing my software, my configuration, and launch it into that auto-scaling group. And as I go through the day, I was staying at that point, and then likewise, my auto-scaling group can have a policy which says, okay, when the CPU average across those two servers has gone down to, let's say, less than 30%, then I will remove the instance that I added in the morning, and I'll be back to one instance. In this way, I can implement Elasticity with some very simple configurations of an auto-scaling group policy and launch configuration. And fronting of Elastic Load Balancer, I can integrate metrics not only like CPU load, but I could integrate things like latency as seen from the Elastic Load Balancer. So as it appears that my website.com slows down, I could add incremental resources. And this way I can have just the right amount of resources to deploy behind the scenes to support the load at a given time. Now, in the real world, this is a customer example in the financial services space, and this is a chart from their systems operations dashboard. So this is real data from a real customer, and we can see elasticity in action. So at this point in time, at T0, let's say, we start at less than 10 cores in operation in their cluster. Now, this is a significant cluster for doing a financial services analysis on market data. And as the market data rates and feeds change, then more and more resources are required to get a computational task done in a given time. So their workload is time-bound. They want to achieve this in a particular time, and therefore they need to grow the pool of resources behind the scenes to deal with the changing market conditions. So 10 cores, and as we move up, 24 hours later, they're running at 1,500 cores in their cluster. So 1,500 virtual cores, and depending upon the instance sizes they're using, that was more or less instances. Over time, that then drops back down to less than 10 cores, and so on up to 600 cores, and we can see a number of peaks that are in the order of 1,000 plus instances. Now, all that white space is time when they've stopped resources. They're not paying for the resources that are stopped, and they have the availability of those resources to start them again and bring them into the cluster as required as part of the elastic nature of their configuration. Auto-scaling is key to this. So clearly we can achieve auto-scaling in a highly manual way. We could just go into the AWS console and start some instances as we see some metric maybe alerting us off CloudWatch to take some action. But by using auto-scaling framework within AWS, we can achieve more or less automation around that. So the first thing we can achieve by implementing a launch configuration, an auto-scaling group, and an auto-scaling policy is then to be able to manually trigger an action against that auto-scaling group. So we can send an API call or use the command line tools to launch or terminate instances as we see fit. So if we have a demand curve that's coming at us, we know that every Friday night that we have a peak of demand, we can simply, before we go home on a Friday night, issue an auto-scaling command to double our capacity in the pool. And on a Monday morning, we can issue a command to scale that back. And we can do that at the command line from a sysadmin's workbench. Equally, we could set a schedule to do that. So we could schedule the auto-scaling group to grow or shrink at times that we know. But more commonly, we do this by policy. So I've talked about CloudWatch and scaling in response to changing conditions. By reading CloudWatch metrics, we can make decisions about what policy actions to apply at a given time. And this can be based upon simple metrics like the CPU utilization, like performance as seen from Elastic Load Balancer, but you can also write custom metrics to CloudWatch. And based upon those that you're writing out of your application, these could be business-aware metrics that you're driving auto-scaling upon. Another function of auto-scaling is the auto-rebalances. So as part and parcel of implementing elasticity and trying to be cost-optimized, you also get a degree of high availability balancing across availability zones. So we'll always make sure that your servers are balanced across availability zones. So a couple of examples here of scaling by policy is based upon metrics from CloudWatch is to double the group size if the average CPU is greater than 80%. And we can do that and ensure that the average CPU is greater than 80% for, let's say, 3 minutes consecutively before we take the action. And scaling down, likewise, would be decrement by, let's say, 10% if the average CPU is less than 30% for another given time. And we could say 1 minute, 3 minutes, 5 minutes, whatever. So we can achieve two policies that work in tandem to grow and shrink our resources to meet just the demand that's coming at us at that time, and to get rid of the resources when the demand has subsided and therefore stop paying for them. But we can also schedule by scale by schedule. So to meet a known demand, common for around batch processing or a monthly peak in ordering on an e-commerce site, you can schedule these things up to 31 days in the future, and you can set a recurring schedule of scaling activities. So another view of that and a typical month-end process. Here I have a chart of the day of the month, so 0 to 30, let's say a 30-day month at the bottom, and we have instance count on the left. And to support a given workload, I've typically got one instance throughout the month to handle a particular load. But at a 3-day period at the end of the month here, I've got the requirement to run 6 instances to run my load. By setting this on a schedule, and rather than having 6 instances provisioned all the time, my monthly predictable peak processing can be hit. I know when this peak of demand is going to come at me. And the traditional capacity would be 6 instances, as shown there in the red line, and the elastic capacity there shown in yellow. Now, the maths behind this shows this is a 75% saving versus running 6 instances in a continual basis. Running 1 and then 6 for the 3-day peak and turning it off again yields 75% cost savings. Okay, so by doing some simple analysis of when you require instances and when you don't, maybe, for example, in the dev test environment, overnight, unless your developers are working on a global basis and maybe sharing environments in different teams around the world, if you're running a dev team that doesn't work through the night, then stop the instances that are running that they are using in those environments, and you will yield a saving in the order of between 30 and 70% depending on what resources are being turned off when. So turn off the lights when you're done. Okay, so that's elastic capacity. Next on our agenda is the instance types that you can use. So there are a whole bunch of instances that you can choose from to run a given workload, and they vary in their family type. So shown here is a few instances. So we have standard small, we have a standard family that goes up to a large. There are high memory and high CPU variants, so where the proportion of CPU to memory changes. We also have cluster compute instances and instances with GPUs. But there are new families being added all the time. So recently we added a new 2nd generation medium family in the US regions, and they'll shortly come to the EU, where we have, again, a different ratio, different performance on the chipsets that underlie these things, the memory allocations, and so on. We also have instances with local ephemeral storage with SSD drives, so that are particularly good for application workloads that require extremely high performance on a disk volume, where you can architect around the fact that it's a non-persistent drive in terms of the life cycle of the instance. So there are a whole range of instances that you can choose from. So choosing the right instance is obviously going to be important in terms of being cost optimized, because the bigger instances you use, the more you'll pay per hour. So to start with, choosing the instance that best meets your basic requirements based upon memory and virtual cores is a good place to start. So if you have an application that you know how roughly it performs on a piece of physical hardware, then match that sort of combination of memory and CPU in an instance in the cloud, and do a little bit of instance testing and seeing how things perform. Then tune. So it's really easy to upsize or downsize your instance size based upon monitoring. And you can use a service called Trusted Advisor, which we'll look at a little bit later, to help you do this. So as part of our support package, we will tell you when your instances are being underutilized or overutilized. And then lastly, spread. So you can achieve high availability for the same price by taking smaller instances and spreading them across availability zones. So without having to increase cost, you can become more fault tolerant at the same time as gathering metrics around how your applications perform on smaller instance sizes, for example. It gives you greater granularity in terms of auto scaling. If you can run your application on smaller instances, you can add increments that are smaller and more granular. But key to all of these steps really is a gathering of metrics so you can understand your position. And knowing your usage is really about using the CloudWatch framework. So an instance with CloudWatch enabled will generate a whole range of statistics out of the box, from free memory, free CPU, free hard disk, and so on. You can push custom metrics into CloudWatch, so your application can post into the CloudWatch API. So you might write business transactions processed or in a queue inside your application, for example, into CloudWatch, and allow that to drive some of the fundamental metrics that you're going to use to tune the instance sizes in play, to choose the density of transactions, for example, you can process on a given instance. And you can do all of this at 1 minute intervals, so you've got quite fine-grained granularity around the metrics that you can gather. All of these things get put into CloudWatch, and then in this example, for example, I'm alerting on a 2-week cycle to send me some information when certain things, thresholds are reached or breached, and that I can then sort of take decisions and around what I do to tune the cycle based upon those metrics and alarms. Now, talking of metrics, you need to really choose the metrics that make sense for your application and your workload, and then you optimize for that metric. So talking generically about what that sort of cycle means is that, for example, you have 3 workloads, and we're trying to understand the cost per unit of work per instance of a given size. So how many pieces of work can we achieve on an instance of a given size, and what is the cost per unit? Okay, now that's what drives, if you like, our computational density on an instance. So here I've got 3 workloads, workload A, B, and C. And workload A may be optimal on a 4 M1 extra large instances, whereas workload B might be optimal on 10 M1 mediums. And workload C might be optimal on an M3 double extra large, on 2 of them. Okay, and what I mean by optimal is that if we look at a simple example here, firstly, I might have the ability to run 10 M1 large instances on the top line, 100 concurrent jobs. Okay, and let's just talk generically about a job and what it could mean to you and your workload. So that job could be the number of users that you can support, the number of processes concurrently that you can run in a batch process, the number of videos you could transcode in parallel on a given instance. So it could mean a whole range of things. But in this case, that means it will cost me $0.026 per job on that instance, versus running on an M3 extra large, which is a new generation of instance that has an instance cost of 0.58 cents an hour. Okay, so nearly or double the price of my M1 large, but I can run on 10 of those instances, and I can run 300 concurrent jobs on those instances. So if we look at the price per job, whilst my instance price seems a lot more, and I might not naturally think that it's going to be cost effective for me to move to that instance, I can actually run a job at 0.019 per job, so I can do it cheaper. So clearly there's a point in time when I need to run more than 100 concurrent jobs and up to 300 concurrent jobs, where I would flip and move to this instance type and make a cost saving to perform the same workload. So think workload density, and don't necessarily focus on the instance hourly rate, because that instance hourly rate, you could get a lot more done with it with the newer instance types than you could on older. So there'll be break-even points. When we look at reserved instances later, there's a similar concept there. Between heavy, light and medium utilization reserved instances. A similar concept applies here when we look at the workload density for your particular workloads. Another way of keeping an eye on what's going on within AWS and the costs maybe per EC2 instance is looking at how we perform billing, and how you can remain aware of the levels of spend that are going on in accounts at any given time. So if you look at a billing structure, typically you have a master account, and that you would have consolidated billing potentially from a division within your company, division B here, that is being passed up to that master account for payment. And division B has an IAM structure of different users and admins, and within there you may be tagging resources. So tagging, for example, EC2 resources with a key value pair to say these EC2 resources belong to this project, to this dev test environment, to this production environment, and so on. And you can have multiple of those sub-accounts being passed up by consolidated billing into the master account. And they've all got their individual tags, they've got their individual user bases and so on. And at the top level, you can gain a view of what is going on. Because we can apply alerts on the sub-accounts. So you can alert when a particular account has reached a particular level, here $500 or $3,000. And then you can generate those as emails to administrators. So if you subdivide your accounts in a way that makes sense for project structures that you're looking to do cost analysis on, tagging the resources properly, putting alerts on them, you can start to get an idea of what's happening. And at the top level, all of that data can get kicked out into S3 as a CSV file that you can put into Excel or your favorite cost accounting tool. And all those tags flow through. So you can have a top-level consolidated view of the price of resources for a given project or a given application. And this is another tool. This is a retrospective at the month-end tool for looking at cost analysis and looking at the process of optimizing what is happening, looking at resources and looking at how you may cross-charge internally for the use of AWS. Now, I mentioned before a tool called Trusted Advisor. Now, Trusted Advisor is part of our support package, and support packages from AWS are an on-demand contract, so it's a month-on-month rolling contract, and you can stop paying at any point in time. You don't have to pre-commit for a year or anything like that. And at the business level of our support offering, it comes with something called Trusted Advisor. And you can get business level from $100 per month for a proportion of your Amazon spend. Now, Trusted Advisor can be found on the support tab of the console, circled there alongside phone support and web support. And when you go into Trusted Advisor, one of the checks out of many checks that we will make for you on your account is cost optimization checks. So this circled is about reserved instance optimization. So this is a Trusted Advisor looking at the instances that are running in an account and saying, in this case, we could save $895,000 by reserving certain instances on a different term. And shown below is the estimated cost of the instances and what you would save if you did a 1-year reserved instance. And we'll talk about reserved instances in a moment and how they work and what they do. Another part of Trusted Advisor is a whole series of checks that we'll make. We'll also look at the utilization of resources. So if you have EC2 instances that are 0.1% utilized on average in a month, we will make a recommendation to you that you should downsize that instance type, because you don't need that size instance type that's running because it's clearly an underutilized resource. So we'll make these recommendations for you that you can go in via the web, and then you can choose to tune your account to come to a better cost basis. So we want you to be cost optimized. It's more efficient for you. It means you'll do more with AWS. It means you'll be a happier customer. And these tools like Trusted Advisor really put the power and the knowledge in your hands to take those actions. Okay, so that's instance types. I promised I'd talk about reserved instances because these are a really important billing mechanism for helping you contain costs. So let's just be clear on how they work and what they do. So we have on-demand instances. So when I was talking about elasticity earlier, about being able to grab a Linux or a Unix server or a Windows server on demand, you're going to pay a price for that instance type as you use it, and when you're done, you can throw it away. So if you like, the classic way of engaging with AWS to get some compute resource. So great for all ranges of use cases. But we have this other concept called a reserved instance. And this is a billing mechanism that sits across the top of your account. This isn't you saying, I want that instance and I want to keep this instance forever and reserve that single instance that I have. This is a mechanism by which you can pay a low upfront fee, but then receive a significant discount on the hourly rate for that instance type. So you choose essentially the availability zone, the size of instance, and the distribution that you're going to use, like Linux or Windows, and in a region, and you would buy an RI for a term of 1 or 3 years. And then when you run an instance of that type in that region, in that availability zone, you will receive a discount. When you stop running one, you won't have any to apply the discount to. So it's a billing mechanism that's applied on the billing system, and we will match any RIs you have to any running instances that match those criteria and apply the discount on your monthly cycle. Now within reserved instances, there are different types you can buy. So you could buy a heavy utilization RI. So if you've got a database server that's running 24/7, you're never going to turn it off. So the utilization of that resource is greater than 80% in a given month. Then by applying a heavy utilization reserved instance for that instance type, you can lower costs by up to 58% for the instance type. So databases, large scale, high performance computing, an always on infrastructure, or the baseline in an elastic architecture would benefit from this type of RI. But there are two other types. There's medium and there's light utilization RIs. So medium and light are really about the time in the month that you're going to be having that resource running or not. So you have a resource that's running between 40 and 80% of the time, then a medium utilization RI makes the most economic sense. And likewise with light utilization RIs, 15 to 40%. And you can see the cost savings there of 49 and 34% respectively. And they'll apply to different use cases or different tiers in your architecture depending upon the demand curve that hits you. So if you look at a break-even chart, these are lines that represent the different types of RIs. Okay, so the red line there is a heavy utilization RI that's got a flat cost to it, and then the others are on demand, where light and medium have different slopes, and then on demand there we can see in light blue. Now clearly you can plot your utilization of a resource at any given time, and we can look at this as an example cost structure of a given instance type. But really what we're talking about is the ability to choose the resource that's right on the white line there. And then I can pre-book that as a reserved instance, and I can yield savings. So the savings there on 100% utilization, you can see clearly between the peak of the light blue line at the top right of my chart and the flat of the white there below is significant. And depending upon the instance size you'll use, that'll be more or less in real terms based upon the traditional hourly rate. And if you look at how you might mix and match the RI types, if I go back to my 24-hour period that I had in my original example, I have a peak of demand during the middle of the day, and I've got a baseline at the bottom that I need to be running something all the time. So shown on the left is a scale of instance numbers. I've got 2 instances running all the time regardless, 24/7, and these are heavy utilization RIs in this case. So I've achieved a cost saving by applying that discount at that level. And then as I go up the tiers, I can see the very peak is a very small peak, so I'm covering that with on demand because that peak may or may not come. But as I go into the purple and the green, these are utilization periods that change and are smaller as I go up. So I've got a green is a medium utilization RI, and a purple is a light utilization RI. By mixing and matching, what we're doing is that as the curve hits us and I need to spin up resources to handle that load, we will then match for the period that I was running that type of resource and it was utilized for X point in time, I'll apply the discount for you, and you can achieve a huge saving on your bill by applying some RIs into your account. Okay, so that's reserved instances, and moving on to a very innovative part of AWS, which is spot instances. So just like on-demand instances, reserved instances, spot instances are about bidding on unused EC2 capacity, and there's a supply and demand marketplace that operates that determines the price of a given resource. Now there's some dynamics of this that make this interesting, and there's some things you need to be aware of if you're going to use spot. So let's have a look at those. So how does this work in terms of our overall capacity within AWS? Now this is an idealized sort of chart, but you think about the reserved instances, there's an amount of capacity that we will keep available for reserved instance purchases, because these are people that are, for example, booking a heavy utilization RI. We know these instances are going to be running 24/7 typically, so there's a portion of the AWS capacity that's given over to those types of instances. On top of that then, there's varying on-demand instance usage, and this will grow and shrink around the world depending upon the time of the day. And then there's a delta at the top, which is called spot. So this is the unused capacity that we're effectively making available at a given price depending on how much is available at a given time, and it's called the spot market. So if you look in your console, in the EC2 tab, you can see spot instances, and then you'll be able to look at pricing history. So this is an example of pricing history around a micro in the US East region across all zones over 3 months. And we can see how the price has varied in different availability zones. And it's varied between not a lot at the bottom to around 2 cents peak at the top. Okay, so around the on-demand price for this instance type. So typically you can receive a capacity in AWS at a significant discount on the spot market. So spot markets, you bid a price. Okay, so you're going to bid a price that you're willing to pay for this resource. So let's say you bid 8 cents in this example, where the current price on the market is 7 cents. You will receive resources. So if your bid is greater than the spot price, you get an instance. Now the thing you need to be aware of is that if your bid falls below the spot price, your instance is terminated. Okay, so whilst you can achieve significant savings, you need to be aware that your resources may be claimed back by AWS if you're no longer bidding the right price and given the market rate for that particular type of resource. Now you can go and programmatically read the price, you can look at the pricing history, and you can make decisions on how you might strategize around the spot market. So given that resources may be pulled away from you at any given time on the spot market, you need to architect for that. So some of the ways in which people do that is that you decouple components. So you would decouple, for example, the front end of your application from the back end, so that the front end would be always running maybe, and back end batch processing could leverage spot. Or using frameworks such as Elastic MapReduce, so a managed Hadoop framework. It's by nature a very fault tolerant framework. You can handle the failure on the spot markets of individual nodes in a Hadoop cluster because the framework manages it. But also you can design with interruption in mind. So by putting SQS queues in place to handle persistence of events, or using things like simple workflow to string together complex workflows without having to rely on the instances to maintain state, because that state could go if they're on spot instances. You can place data in durable stores such as S3 or SimpleDB or DynamoDB and effectively save your progress regularly on a given task. Then you would be able to leverage that very low price of spot, yet able to tolerate some sort of failure of that node when we reclaim it if your price doesn't go favorably for you on the market. Having a look at an example of how this works and how this can achieve quite an interesting dynamic is that with Elastic MapReduce, they're pretty much a sort of a near linear scale. So in this scenario, I've got 4 instances to do a computational task, and let's say that task takes 14 hours. And for sake of argument, my price on demand for that instance type is 50 cents. So 4 instances for 14 hours at 50 cents is $28 to get this particular job done. Maybe it's a big computational task such as counting the number of records or instance types of a record within a very large log file that is split up across 4 instances. Now scenario 2 around that same job is that I could add 5 spot instances, and because it's a near linear scale, I've pretty much doubled the resources I have available to the job. So I halve the duration of this EMR analysis. And if I do the costing around that, I've got my original 4 instances at 50 cents, but for half the time. So I'm doing that for $14 versus the $28 previously. And I have 5 instances, and let's say that my spot price at this is half the on-demand price. So my spot price here is 25 cents. So 7 hours, 5 instances at 25 cents is $8.75. Add the two together, and I've got a cost of $22.75 versus $28. So with the spot market, and by wrapping it in a framework such as EMR that enables me to be fault tolerant, I've done more for less. So I've saved time, I've done it in half the time, and I've saved 22% on the costs. So pretty good for paying less and getting something done quicker. And this is something that you can achieve in your own architectures by using Spot too, because you can create highly parallel workloads, and if you're fault tolerant to those failures, or you implement a bidding strategy that enables you to manage that and to reduce the risk of that, you can achieve some significant cost savings. So let's look about some of the bidding strategies that customers use. If we look at some real data from the spot market within AWS, the bid distribution for a 3-month period here, we can look at the bid price as a percentage of the on-demand price and the percentage of the distribution that's gone. So we can see the blue bar in the middle is people bidding on the on-demand price, 100% of the on-demand price. Whereas at the far right, we've got people bidding 200%, twice the on-demand price. And at the far left, people bidding only 30% of the on-demand price for that given resource. So that explains the chart. Now, if I look at what people are doing, we've got a portion of people down at the bottom there that are bidding near what is actually the reserved instance hourly price rate for a given resource. As we move to the right, we have people bidding above the spot price history for that given resource. So they're trying to follow the spot price on a given period of history. We have people that are bidding near or the on-demand price for that particular resource. So they're prepared to pay up to what it would cost them normally to get this resource on the spot market. And at the right, we have people bidding way above, in this some case more than twice, the on-demand price. Now this brings together some various different strategies that we see customers using. So the first is bid near the reserved hourly price. You only pay for a full hour. Now this is a dynamic of the spot market, which is interesting. So if you can tolerate failure, if you are interrupted on an instance within the hour, you don't pay for that hour processing. Now on demand, if you take an instance and then drop it 30 minutes later, you will pay a full hour for that instance. But for spot, if we interrupt you, you don't get billed for that portion of the hour that the instance was running. So if you bid at a low price and you can tolerate failure, each time you're interrupted, you will get effectively some free processing. Now there are customers that are able to accept a high degree of interruption that will bid very close to the bottom price or the market price at the lowest point, and they will accept interruption because they're ultimately getting extra resources for free as part of the process. So an extreme example, bidding near the reserved hourly price. So if you're interrupted, the hour is free. Another example is bidding above the on-demand price. So if you bid at a level that is significantly more than the on-demand price, then over given history of the spot market, you can make a fair assumption of how often you think you'll be interrupted, and it will be far less than if you bid at a lower level. So we saw on that previous chart that customers were bidding 200% or more of the on-demand price because they're only paying for the spot price at a given time. They're bidding at a level which means that if the price does rise above on-demand for a given period, maybe for a day or two, they will pay more for that period than they would have on the on-demand price market. However, for the remaining period of time, they're paying only what the current spot market is priced at, which is typically significantly less than the on-demand price. So net-net, they're still making significant savings, and they're reducing the risk of interruption by doing that sort of bidding strategy. Another thing about customers that are implementing on the spot market is that they are embodying that implementation of a cost-aware architecture, because their applications will be taking feeds of the spot market price for a given instance type, and they're able to flip from spot to on-demand as price dictates, because they've architected in a way that their systems can be interrupted. They've architected in a way that enables them to automate the creation and destruction of resources. And by having applications that read the spot market and decide when the market price is moving in a way that's non-favorable, they can move processing from spot resources to on-demand and then back again when the prices move back in the favor. And there are customers that are really doing this, and that they are leveraging the automation within AWS to enable to do this and to achieve huge cost savings whilst not being interrupted as part of their workloads. Some customers that are using the spot market extensively, a range of them here, from academic institutions to popular video encoding sites like Vimeo and sharing sites. But an interesting one at the top right, which gives an example that you could implement yourself that may be useful to you, is BrowserMob. So BrowserMob is an online testing tool where you can load test a web application, and part of that load testing you can spin up many hundreds of real instances or servers running real browsers, maybe running a Selenium script, for example, in that browser, and they will run up on the spot market instances for you to do that. And you will therefore, as a customer of Browser Mob, receive some sort of saving over doing that traditionally. Now they're doing a concept that you could do yourself. So you could spin up resources on the spot market to perform load testing, to perform more real world testing in a way that you wouldn't maybe economically be able to do with on demand. You couldn't justify the price. On the spot market, it becomes cost effective to do so. And given that you can spin these up every 2 or 3 hours, run a load test for a couple of hours and then turn them off, it's a great way of performing some testing that you couldn't do in an on-premise environment through capacity constraints as well as for economic reasons. Okay, so that's spot instances. Lastly, complementary services. So a short section here of talking about software versus services. So if we look at a classic stack here at the top of using an elastic load balancer to front some web servers across multiple availability zones and compare that to running a software load balancer at the bottom on an EC2 instance, I'm trying to draw the comparison of using load balancing as a service versus installing load balancing as software on an instance. Now, load balancing as a service costs us 0.028 per hour for you to use an ELB, versus running that on a small instance will cost you 0.08. And if you look at what can happen behind the scenes there as well, is elastic load balancer is multi-availability zone, whereas a software load balancer is inherently in one availability zone. So the idea being that there are services within AWS that you can achieve cost optimizations from moving software that you might install and run in AWS and moving that function onto the AWS equivalent service. And there's a range of those that you can use. Another example would be SQS. So queuing is a common architectural component for use for decoupling tiers of an application or functions within an application. So we might produce a message from one system, like an order taking system, drops a message on SQS queue, and then there are boxes or instances that consume those messages to process maybe an order or a video encoding job and so on. And SQS is extremely cost effective because it's 1 cent per 10,000 requests. So extremely cheap to manage persistent message queues at a regional level within AWS. Versus, again, having to install an instance, install a software queue, and do the same. So software on EC2, of course you can install software. You can get any software you like and run it on EC2. And you can use all the custom features, and you can implement the latest of a framework. You can implement commercial software and so on. So it's a great thing to do. However, it does require some effort. It requires an instance. It has a cost associated to it. It will generate typically a single point of failure in your architecture because it will generally be limited to one availability zone, and you need to administer it yourself. Okay, so just like any other sort of software stack in any other environment. AWS services like Elastic Load Balancer, like Simple Notification Service, a Simple Queuing Service, Simple Email Service, Simple Workflow and DynamoDB, and more, what you're getting is a pay-as-you-go, typically a much better price than running it yourself. And then to boot, you're getting scalability, availability, and high performance as part and parcel of consuming that service. So there's a whole range of services that that I haven't mentioned here, things like Cloud Search, for example. Rather than installing an open search engine across a cluster of instances in your environment, you can simply consume search as a service, get high performance, take away all that pain of management, and save yourself a whole bunch of money along the way by consuming it in that way and letting us run it for you and removing the EC2 instance costs. Okay, so closing off our webinar today. So in summary, we've talked around elastic capacity, really about turning things off when you don't need them and only bringing on new resources as you need them. And that can apply equally to a dev test environment where you simply turn stuff off at night when you're not using it, as it does to a production environment where you bring resources on via things like auto-scaling as you need them, as well as throwing them away via auto-scaling. We looked at instance types, so choosing the right instance for the density of the workload that you're performing, and to put some thought behind the metric that you're collecting and going to analyze against, because you may find that a different instance type gives you a better cost-effective overall for your platform than maybe the hourly rate of that instance type dictates. The reserved instances, so a great billing mechanism for reducing your costs and using things like Trusted Advisor to get some advice on that. Spot instances for workloads that you can tolerate interruption on, or where you're prepared to put the effort in to understand the spot market and to develop a bidding strategy that works for you. And of course, not running software on EC2 instances, but rather consuming services where they're available in AWS will save you money too. So where to go next? There's a number of resources that we can point you to. So there is an economics section on the aws.amazon.com website. And there's also a calculator at /calculator. So advise you to go and have a look around in there. Within the economics section and also in the white papers section, there is a number of papers, and one of those is how AWS pricing works. So we'll go into a lot of detail around this, and there are economics papers around the TCO of cloud, building the case for cloud. But also all the topics that I've covered today will be generally covered in one or more of those white papers in terms of how to strategize around using AWS and some best practice advice on keeping costs contained. And just a quick view, the cost calculator that I mentioned, simple monthly calculator, you can leverage some templates in there that will generate typical web application framework sort of structures, or maybe batch processing structures, and it will give you an idea of what resources are required. And you can tune this to a high degree of detail. So you might want to tune the amount of data that you think you're going to get in and out of an application, for example, and it will chart up all the different parts of the bill and estimate your monthly bill that are coming out. And you can add RIs to that, for example, and see how that compares maybe if you were to make an RI purchase. So take a look at the cost calculator. Find out more, as always, at aws.amazon.com, and do let us know what you think about these webinars. Drop us a note on the Contact Us form on the website.